Okay, so now we will continue with our thematic session. I have the pleasure now to present Cristina Lizana. Cristina was a student of Enrique Pujals, and after doing some postdocs and actually going back to her home country, which is Venezuela, she now holds a position at the Universidade Federal da Bahia. So welcome, Cristina. She will talk about robust transitivity and domination for endomorphisms displaying critical points.
Thank you, Yuri. So for me, it's a pleasure to be here today. I would like to thank the organizer and to congratulate for all the event. So I'm going to talk about a joint work with Rafael Potri, Enrique Pujals, Wagner Hunter, sorry, I'm having to interpret with Portuguese, Spanish, and so on. So I'm going to talk about robust transitivity for endomorphisms. So I'm going to set all. So we are going to work with C1 endomorphisms in compact boundaryless manifolds. And our goal is to find necessary condition and topological abstraction for the existence of robustly transitive maps. So let me define some words, some notion we are using here. So transitive for us means that there is a point with forward orbits dense. Robustly, we are thinking the C1 topology. So if you have a transitive map, there exists a C1 neighborhood of this, where every map here is transitive. And so we would like to know which are the necessary conditions in order to have the existence of this kind of system. So let me talk about the state of the art. So for diffeomorphisms, that is the very well-known setting, no? So I'm not here in the chronological order, but I'm ordering the for dimension. Okay, so in dimension 2, we know the very well-known result from Magne, that he proved that the robustly transitive diffeomorphisms are equivalent to an also. So you have this hyperbolic structure in the whole manifold. And he got a stronger result. Actually, he find which surfaces admit this kind of system. So there are some examples from Schub and Magne, where they construct these robustly transitive diffeomorphisms that are not hyperbolic, but they are partially hyperbolic. So we are having a student here probably. So a hyperbolic, I meaning that you can decompose. You have a splitting of the tangent bundle in at least two subbundles. One is contracting and the other is expanding by the derivative. And partially hyperbolic, you have an extra subbundle where you don't have a uniform behavior. So these two examples of Schub and Magne, they are partially hyperbolic, so you can decompose in three subbundles. And you have a contracting, you have expanding, and you have a central subbundle. So Magne, derived from an also, is very well-known example, is in dimension 3, and the Schub example is in dimension 4. So I'm trying to relate the notion of robustly transitive with this notion of some behavior in the tangent bundle. There is another example, a little bit recent, from 2000, Bonatti and Viana. They show a robustly transitive diffeomorphism that is not partially hyperbolic, but is the tangent bundle admit an splitting that is called dominated splitting. So you decompose the tangent bundle in the direct sum of two subbundles, where you don't have uniform behavior in the sense that you don't have a contracting and expanding behavior, but one of them dominate the behavior of the other. So in this sense, the question is, what is a necessary condition to have roughly transitive for the diffeomorphism setting? So the result of Diaz, Pujas, Ures, and later Bonatti, Diaz, Pujas, they prove that if you have a C1 robust transitive diffeomorphism, then your manifold admit the dominated splitting. So you can decompose the tangent bundle in the direct sum of at least two subbundles, where one dominates the behavior of the other. So I said at the beginning that we are working with endomorphisms. So let's see what happened for local diffeomorphisms first. So there are some very well-known examples of the SHUPs, the expanding maps. So they are transitive, they are robustly transitive, and if you perturb any expanding map, you still continue having this this property, and you can decompose. Since it is expanding, your tangent bundle is going to be you can decompose, but with expanding behavior. And Gromov proved that the only manifold that admit this kind of map are the infranil manifolds. So remember that we are also trying to find some topological abstraction. So in 2013, we published with Pujas. This is a result from my PhD thesis, that we gave some necessary conditions, necessary and sufficient condition to have robustly transitive local diffeomorphisms. And one of these necessary conditions is in the local diffeomorphism setting is that you have to be volume expanding. So actually, remember that for diffeomorphisms, I said that you have a necessary condition that your tangent bundle has to admit the dominated splitting. But for local diffeo, this is not true anymore. I mean, you can construct an example of a robustly transitive that doesn't admit any kind of splitting, so you cannot decompose the tangent bundle. It is very easy. For instance, you start with an expanding map, and you make a surgery to the eigenvalues become complex, so you destroy any invariant direction. So it is not necessary for this setting to have a weak form of hyperbolicity, but you need some volume expanding. Okay. So now what happens if you add some critics? I mean, for critics, now you are having points where the differential at this point is not an isomorphism. So you can have the kernel of this, the differential in this point are not trivial. So you have direction where the isomorphism is going to be 0. So you have some natural question in continuing the last result I just said, I just mentioned. You have, for instance, you can ask you which homotopy classes admit this C1 robustly transit endomorphisms, displaying critical points. For instance, which kind of manifold support these maps, these systems, and also what is a necessary condition? No? Is it necessary to have this weak of hyperbolicity? Remember, for diffeomorphisms, it's necessary to have a dominated splitting. For local diffuse, it is not necessary, but surprisingly for critics, we are going to recover this property for diffeomorphism. So let me talk a little bit about the examples on surfaces. There are a couple of results of Berger Robella and Iglesia, myself, and Portela, where we construct some examples of grossly transitive endomorphisms, admitting critical points in the homotopy class of a hyperbolic linear endomorphisms. So you start with, this is on surfaces, so we are working in dimension 2. So for instance, you start with a linear hyperbolic endomorphisms with 2 eigenvalues, and one larger than 1 and the other larger, less or equal to 1. And you can construct endomorphisms that are homotopic to the initial one, and they are C1 robustly transitive. They admit some unstable family of cones and also persistent critical points. So later with Wagner, we construct some examples in the expanding homotopy class and for the 0 degree class. So when I mean for the 0 degree, remember that we have a matrix of 2 by 2. So we have one eigenvalue larger than 1. Actually, I forgot to put it here, but the lambda is larger than 1, and the other eigenvalue is 0. So we also construct some examples that are homotopic to these classes, and they have all these properties. So they are robustly transitive, they admit persistent critical points, or they have a family of unstable cones. This property, that the dimension of the kernel has to be strictly less than the dimension of the manifold, is a necessary condition for our setting now. And all these examples exhibit the weak form of hyperbolicity. So we are answering here the first question. So we at least these all homotopy classes, they admit this kind of maps. So remains open the case that when you have one eigenvalue of multiplicity 2. So I mean, you have, for instance, a 2 by 2 matrix, and you have lambda are the eigenvalues. So we are assuming here you have here one direction that is strictly more expanding than the other. So what happens if you don't have this situation? We still don't know if you can construct this kind of system. But this condition of the dimension of the kernel is a necessary condition. So if you, for instance, you have the dimension of the kernel, a full dimension, so it means you have a point that is a super attractor, and you can perturb, you can find an open set of critical points where all are attractors, and you destroy now the possibility to have the transitive map. Okay, so remember that for diffeomorphism, our abstraction for having a transitivity where the attracting and repelling points. And now for the endomorphic settings, our abstraction for transitivity are going to be the attracting points and the full dimensional kernel of the differential. So,
Cristina,
yes.
sorry. A very quick question. What is the manifold you are working on? You're always on the torus in these results, or what's the manifold?
In this result, we construct the example. The first one here, Bergera, Rubella, Iglesia, they are on the torus. And the example with Wagner, we construct actually an example on the torus and the claim bottom.
Okay, thank you.
So actually, we prove with Wagner that the only surfaces that admit this kind of maps are going to be the torus, the two torus, and the claim bottom. So,
you mean this kind of conditions?
So if you have a roughly transitive endomorphism with critics.
Okay. Very good.
That is in dimension 2. Yeah. So here is what I was mentioning. This it was recently published in the Advances in Mathematics with Wagner. This was part of his PhD thesis also. And we prove that if you have a roughly transitive endomorphisms and you have critics, you have points where your differential, the kernel, the differential is not trivial, then it has to be partially hyperbolic. So we are recovering this condition of the weak form of hyperbolicity. So now what it means partially hyperbolic for us, you have a decomposition of the tangent bundle in the direct sum of two spaces, two subbundles. One is the central dimension, the central direction, and the other one is going to be actually an expanding direction. So you have a central unstable bundle. So here, the idea of this, to prove this result, is you have the direction of the kernel. Remember that we had it's necessary that the dimension of the kernel, the differential is one dimension less than the manifold. So if you have in dimension 2, it has to be at most dimension 1. So you have one direction that is going to be induced by the kernel of the differential. And now the other direction, you're going to have a candidate that is the transversal direction. And so you have to build in a very clever way a family of unstable cones that is going to be to give you the splitting. So more or less is the idea. So I very rudely speak. So I have 40 minutes, yeah. So it's not. How much time do you have?
You have until 20? 51. So you have 17 minutes.
Okay, so in this work, we prove with Wagner that the only surfaces that admit this kind of maps are the two torus and the claim bottom, as I was mentioning in the example. And this implies immediately that we don't have any robustly transitive map on the two spheres. So that answer a question that we were mentioning before. So also we prove with Wagner that if you have a transitive map endomorphisms with dominated splitting, it has to be homotopic to a linear map having at least one eigenvalue with modulus larger than 1. So this is going to imply that there are no robustly transitive surface endomorphisms homotopic to the identity. So at least one of the eigenvalue has to be larger than 1. So the question is what happened in higher dimension? Okay, so in higher dimension, we are the joint work with Patrick, Pujarz, and Wagner. We obtained that if you have a dimension larger than 3, every roughly transitive endomorphism displaying critical points admits a non-trivial dominated split. So, as I said, we are recovering all these geometrical behavior of the diffeomorphisms. For diffeomorphisms, we said, okay, every C1 robustly transitive admits a dominated splitting. For local diffeo, again, we don't have this property always, but now for when you have critical points, you recover this property again. So as a consequence of our result, we got that even dimensional sphere do not admit robustly transitive endomorphisms. Okay, so I'm going to give a sketch of the proof of theorem A to give some idea of the techniques. So so I should say something before I give the sketch. When you are for the diffeomorphism setting, or the classical result, they use strongly the periodic points. So they show, for instance, Magnet, they use some classical result like a closing lemma and connecting lemma, that we don't have this result for endomorphism setting. So we cannot use these techniques. And he also used strongly that the system of the periodical points, and he construct the splitting over the periodic points, and then use the fact that the sinks and the sources are obstruction for transitivity, and he can extend this splitting for the whole manifold. So for us, we are going to use strongly the existence of the critical points. Okay, so the idea is the following: you have you start with a robustly transitive maps displaying critical points, and you choose a neighborhood of this endo, where every map here is transitive. This is C1 neighborhood. And you use now the fact, you use now the fact that you, the kernel of the differential cannot be full dimension. If you have again, in dimension 2, the kernel is at most dimension 1. In larger dimension, from point to point, the dimension of the kernel could vary. But when you look at now at the here, what I'm defining as the dimension of the kernel is the maximum of the dimension of the kernel at each point. So when you look at this maximum, this is bounded for a number that is strictly less than the dimension of your manifold. Okay, so this key lemma is going to be very useful for us in order to construct the splitting. So the initial map, it can be approximated by a map that is satisfying the equality before here. So you had the dimension is less equal than kappa, and I say you choose F where you have the equality, so you can approximate your initial map by a sequence of map having the equality, and you let us call MF exactly the time where you have this set has no empty interior for some point. And in case that this set has empty interior, then you take this number as the smallest one where you have equality. Okay. So for every kappa, for this number kappa, we define the set CR kappa as all the point where the dimension of the kernel is exactly kappa. So this set, you are considering the critical points. Okay, so you are considering critical points. And this set has the possibility to have empty interior. So I'm choosing a new set of the endomorphisms of all the endo in our neighborhood, where this set has non-empty interior. So what happened is, so the natural question, okay, why you have that is non-empty? No, the interior is non-empty. So if you can use the Frank lemma to approximate. Let's see, if you, in the case that you have an empty interior, you can perturb in such a way using the Frank lemma that you get a new map where this set actually has non-empty interior. Okay, it's a very technical part, but you can believe me that actually this set F naught is not empty. Okay, so you actually have maps here in this neighborhood where the interior of this critical set is non-empty. So now, for every map in this set F naught, we define this lambda F set, where basically you are choosing full orbits, where you have that there are infinite points in this orbit that they enter in the critical set for the past and the future time. So this set is intersecting the critical set. So it's what I was saying at the beginning. So now for us, we are using strongly the existence of the critical points, and they are our best friend now. So they are going to allow us to construct now the splitting, the candidate for splitting for this set. So again, how we are going to use, remember that you have a direction associated to the critical point where you have the kernel. And this will induce a subbundle that is associated to this kernel. And now you have a complementary direction that is going to give you the splitting, that is actually going to be a dominated splitting over this set, the lambda F. So for this, we construct again a family of cons, but now we are not able yet to say that this is going to be expanded. For higher dimension, we know that is a dominated split, okay? So we are not able to say that it's partially hyperbolic. So the last part to conclude the result is the following. You had the splitting over your lambda F set. Now, using the fact that F is transitive and this set here is not empty, you prove that the lambda F set is a dense set in your manifold. So this splitting, you have a control of the angle between the subbundles, and using the density of lambda F over the manifold, you can extend this splitting to the whole lambda F, to the closure of the lambda F that actually the manifold. So that is basically the idea.
Cristina, just one question.
Yes.
This lambda f is a subset of M or a subset of the natural extension?
Yeah, actually it's in the inverse limit, exactly. So I'm getting the full orbit here. Mm-hmm.
And it's going to be dense in the inverse limit as well?
Yes, it's going to be dense in the inverse limit. Mm-hmm. So using that F is transitive and this set is non-empty. Mm-hmm. Yeah. So using this, you get that our result. So you construct actually the dominant splitting for the whole manifold. So you need some technical result to control the angle between the subbundles, no? And to prove that they are actually invariant subbundles. And you have the domination property also, no? But all the proof, the ideas, I mean, you have to construct some family of cones and work with this in a very clever and careful way. So probably I have. So in this setting for higher dimensional, we are not able to conclude that F actually is expanding, but we conjecture that if you can split in one-dimensional subbundles, the extremal one probably is expanding. So at least it's volume expanding. So that in the more or less following the ideas of Bonatti-Diaz-Puhal, that when you decompose the subbundles in the finest dominated splitting, the extremal one are volume hyperbolic. So that is what we conjecture here for in the case that you are considered the finest dominated splitting. So I don't know if there are some questions. I cannot see the chat. So that is all I want to say.
Okay, thank you. Thank you very much, Cristina. We already have here one question from this guy called Lorenzo Diaz. He asks, how is obtained the candidate splitting?
So in dimension 2, the candidate, it's easy to see that is the kernel, the kernel of the differential. When you are in higher dimension, now you have to be careful because changing from point to point, the dimension is going to be different. So for instance, in one point is dimension 1, in another point is dimension 2, and probably is getting. But when you look at the maximum, you know that this is strictly less to the dimension of the whole manifold. So you look at exactly at the point you are looking, remember here, exactly the point where you have the equality. So now this is the candidate. You look at the points where you have this exactly kappa dimension, and this is going to be your candidate for the E subbundle. And then you are going to construct your family of cones in the complementary dimension. So it's more or less the idea. I don't know if Florence is happy with my answer.
We will know soon. There is another question by Amino Zadat Talebi. He asks, what about robustly non-transitive maps? Which examples are known?
Non-robustly transitive maps?
Yes, so I think he's asking about the complement of the open set defined by the complement of what you talked about.
Yeah, actually, I have no idea. I haven't think about that.
Oh, may I ask a question?
Sure.
Cristina, we know that on three-dimensional sphere, we don't have partially hyperbolic diffuse morphisms. You are going through the direction that when you have criticality, endomorphisms satisfy similar results. First question: do you have any example of robustly transitive on three-dimensional sphere? Do you expect that there exists or not?
That is a really hard question. So
you see, it is as difficult as in the case of diffeomorphisms.
Yeah. Actually, we expect they are not, but actually we don't know, and it's a really hard question. I mean, if somebody want to try, it should be a very interesting point. So we prove that if you have dimension that is even, so you don't. But I don't know what happens in dimension 3, actually.
In principle, you don't have even this machinery of foliations. Am I right?
Yeah.
Okay.
Yeah.
Okay.
Mm-hmm.
It's more difficult to prove non-existence, maybe.
Yeah, actually.
So Lorenzo said that he's happy with your answer. And Pablo just mentioned that actually example of robustly non-transitive is any map with a sink. If you perturb, you continue to having a sink there, and it is certainly non-transitive. So we have Maria José Pacifico's question also. Did you classify the manifolds presenting this type of dynamics?
For higher dimension, no. At least we know that if there are spheres, even dimensional, we don't admit this kind of map, but we don't have a topological abstraction yet.
Okay.
Just in dimension 2.
Okay, so if there are no more questions, we should thank Cristina again. Sorry.
Let me ask a silly question. So, why the existence of critical points really help in the proof? Because the result is not true for, without the assumption of the existence of critical points. So what is in resume the philosophy behind this?
So if you don't have critical points, you can make this that I was saying, no? You make a surgery and put some complex eigenvalue and destroy all the invariant direction. So now if you have critical points, you know that certainly you have one direction where your derivative is not expanding. I mean, actually it's not an isomorphism. So this direction, you cannot make this again, the game that you put this complex eigenvalue. So you are going to keep this direction that is associated to the kernel of the critical points.
Okay, thank you. So you have a special direction given by the kernel. So thank you.
Yeah. If you had the existence of critical point, you have one direction that is associated to the kernel. So that is the key of the result.
Okay, So we are short on our schedule. So let's thank Cristina again.
Thank you.